Okay guys, welcome to today's lesson. Today we're going to be covering gas stoichiometry. These are reactions that do not occur at STP, so we're not multiplying by 22.4 liters. These involve the ideal gas law. So to refresher, ideal gas law is PV equals nRT, where pressure is represented by P, V represents volume, N is number of moles, R is our constant, our gas constant, which we know is always 0.0821, and it has units of atmosphere, liter, per mole, Kelvin. And then our temperature is always in Kelvin. So, if we have given a temperature in Celsius, we can convert it to Kelvin by simply adding 273 to that temperature in Celsius. Now, in some college courses, they might add 273.15, but for today's lesson, we're going to keep it simple and just stick with 273. All right, so we're going to jump in to the first problem, number 10, which says, ammonium sulfate, an important fertilizer, can be prepared by the reaction of ammonia, which is NH3, with sulfuric acid, H2SO4, according to the following balanced equation. So for this problem, they give us a balanced reaction. They won't always do that, but for this problem to get started, they do. And the directions say, calculate the volume of NH3 in liters needed at 20 degrees Celsius and 25 atmospheres to react with 150 kilograms of H2SO4. So, what I like to do to get started is go ahead and simply identify what we know. All right, we know we have a temperature for ammonia. All these quantities are for ammonia, so just make a little note of that. We have a temperature value of 20 degrees Celsius, which when we add 273 to that, we get 293 Kelvin. We have a pressure we're given for ammonia as being 25 atmospheres, 25 atm. And we're asked for the volume. That's our missing variable, that's our unknown, so we'll put a question mark for volume. We always know R, so the last item we need is N, number of moles of ammonia. This is where the stoichiometry is going to come into play, where we take the mass of sulfuric acid we're given, H2SO4, convert that to moles, and then to moles of ammonia. So, we're given a mass for sulfuric acid, H2SO4, as being 150 kilograms. Notice units of kilograms, very important. In chemistry, we need to be in grams. Physics, we might deal with kilograms as our base unit. In chemistry, we convert to grams. Remember, there's 1,000 grams in 1 kilogram. So we multiply by 1,000 to get 150,000 grams for sulfuric acid. Now for the stoichiometry. Now we need the number of moles of ammonia, NH3. All right, so I'm going to convert that by starting with my 150,000 grams of H2SO4, and I need to calculate now the molar mass. If you'll recall, when we do our conversions, all right, if we can go back to our diagram of the molehill, at the top of the hill we have 1 mole. At the bottom we have our mass in grams. What connects those two is the molar mass. If we're going up the hill, we divide by the molar mass. If we're going down the hill, we multiply by the molar mass. So in this case, we're going from mass to moles up the hill, so we're going to divide by the molar mass of H2SO4. Okay, we can go to our periodic table to calculate that molar mass. We have 2 hydrogen, so we have 2 times 1.01. We have 1 sulfur, which is 32.07 when we round. And we have 4 oxygen, so 4 times 16. When we add all these up, we get a molar mass of 98.09 grams of H2SO4 per 1 mole of H2SO4. So, if we use our molar mass now, we can simply divide by the molar mass, or multiply by 1 mole, and divide by the 98.09 grams. This step will get us to moles of sulfuric acid, the H2SO4. Now, to get to moles of ammonia, recall we need moles of ammonia, we have to multiply by the mole ratio, which comes from the coefficients in the balanced chemical equation. So we're at moles of H2SO4. We need to get to moles of ammonia. We see for every 1 mole of H2SO4 consumed, sulfuric acid being consumed, we're consuming 2 moles of ammonia. So we're going to write our moles of H2SO4. This goes in the denominator here. And we can see SO4. For every 1 mole of being consumed, we're consuming 2 moles of ammonia, NH3. Alright, so when we multiply across, we'll just move this down here. We multiply across, we figure out that we have 3,058.4 moles of ammonia, NH3. Okay? So, now we have our number of moles of ammonia. All right, 3,058.4 moles. So we have our pressure in number of moles. We have the R constant and temperature in Kelvin. We can plug all these variables in to find our volume. So I would simply start off with my pressure being 25 atmospheres. We're solving for V, our volume, unknown. That's equal to number of moles, which we know is 3,058.4 moles. Okay. We know R is our constant. It's always 0.0821, and it's got units, particularly units of moles. I should say atmosphere liter over moles, Kelvin. And we have units finally for our temperature as 293 Kelvin. Okay? So this is our equation to solve for V, our volume. We can simply divide both sides by the pressure of 25 atmospheres on both sides. So we divide by 25 atmospheres on both sides. That'll cancel on the left side. So we can cancel on the left. On the right side, notice moles per moles cancels. Kelvin per Kelvin cancels. And finally, atmosphere over atmospheres down here cancels. So we're left with units of simply liters, which is going to be our unit for volume. So when we multiply across and divide by our 25 atmospheres, for our volume, we get our answer as being 2,942.8, which we'll just round up to 43 liters of NH3 ammonia. Okay, so this is our volume of ammonia that we produce, or that we would actually be required to react to produce the ammonium sulfate fertilizer. All right, so quick review. We convert our mass given to moles of ammonia using stoichiometry. We use that number of moles with our temperature and pressure given to solve for the volume of ammonia. Okay, this is number 10. This is obviously a problem that does not occur at STP. It wasn't as simple as simply multiplying the number of moles times 22.4. We had to take into account the varying pressure and temperature. Okay, so that is our first problem. All right. Okay, moving on. All right, moving on to our next problem. Next problem, number 11, says if 45 liters of natural gas, which is essentially methane, CH4, undergoes complete combustion at 700 millimeters of mercury, 730 millimeters of mercury, and 20 degrees Celsius, how many grams of each product are formed? All right, so this problem is going to require us to first write out the skeleton equation and then balance it, write out the balanced chemical equation. So, the general formula for combustion, we have to know this, is always going to be a hydrocarbon plus, which is always made of, as you might guess, hydrogen and carbon. So hydrocarbon plus oxygen in the gas form is always going to yield carbon dioxide and water, and of course energy for combustion. We don't count that. So in this case, this specific case, we're given a hydrocarbon of methane, CH4. All right, so that is going to react with oxygen gas, which is diatomic by itself, O2, to produce carbon dioxide, CO2, carbon dioxide, plus water, which we know is H2O. Now, when I balance combustion reactions, I always balance the carbon on both sides first, then the hydrogens, and finally you want to balance the oxygen last. Now, this one would say is pretty straightforward. We have one carbon reactant, one carbon product. We have 4 hydrogen reactants. So to get 4 hydrogen products, we'd simply put a 2 coefficient here. We now have 4 hydrogen reactants and products on both sides. And now to balance oxygen, we have 2 here and 2 here. The coefficient would give us 4 oxygen products. So in order to get 4 oxygen reactants, we simply put a 2 here, and now our combustion reaction is balanced. Okay? So, let's look at the rest of the problem. It says we're given a volume of natural gas, a volume of methane. Okay, so we're going to be using the ideal gas law. So just go ahead and write that here as a reminder. Okay, PV equals nRT. We know R is always equal to 0.0821 atmosphere liter per mole Kelvin. Okay. We're given a pressure in millimeters of mercury. Now this is important. Notice our constant R has units of atmospheres for pressure. So we need to convert our pressure given in millimeters of mercury to a pressure in atmospheres. We can do that by knowing 1 atmosphere is equivalent to 760 millimeters of mercury. This is our conversion factor between atmospheres and millimeters of mercury. So, when it says the pressure is 730 millimeters of mercury, I can simply multiply by 1 atmosphere to get atmospheres as our unit of pressure, and divide by our conversion factor of 760 millimeters of mercury. All right. When I do that, I get a pressure of approximately 0.9605 atmospheres. Okay. We're given a volume for our methane as being 45 liters. Okay. And a temperature at 20 degrees Celsius, which if you'll recall, we can add 273 to get 293 Kelvin. All right. How many grams of each product are formed is the question asked. So we're going to do some stoichiometry here. We're going to take our pressure, volume, temperature, and R to calculate N, the number of moles of the methane that's consumed, I should say, being consumed as reactant. Then we're going to calculate that using the ideal gas law. Once we have that, we can then use our number of moles of methane and do some stoichiometry to calculate the moles and finally mass of carbon dioxide and water as our products. So, we know our equation, ideal gas law, PV equals nRT. All right, we have our pressure, we it's 0.9605 atmospheres. We have our volume at 45 liters. That's equal to our number of moles of methane we're trying to find. Okay. Multiplied by our constant R, we know is 0.0821 atmosphere liter per mole Kelvin. And finally, we have our temperature, we know is 293 Kelvin. Okay, so we can now divide by our pressure and volume on both sides, and we will get, I should say, take that back. We can now divide by our constant R and our temperature on both sides, and we will solve for our number of moles in. Oops, and we're missing a 1 here. Okay, so we can divide. If we know first our Kelvin will cancel, we can cancel our Kelvin. Okay. If you like to, you can multiply these two first together and divide by this as a single number. I'm just going to write it all out. 0.0821 atmosphere liter per mole times 293 Kelvin. We get the same thing on this side. We have 0.0821 atm liter per mole times 293. Notice the Kelvin cancels on this side. We already canceled the Kelvin. Okay. So notice now atmospheres will cancel atmospheres down here. Liters will cancel with liters down here. The moles will flip up, so we'll get units of moles. And when we do this, we multiply these two, divide by this, divide by this. It's two separate steps in the calculator so that it divides separately. We will get a number of moles equivalent to about 1.8. So about 1.8 moles of CH4 methane. Okay, I rounded this as 1.79 with some trailing decimal. We'll round this to 1.8 moles of methane. So this is the first step. This is step number 1. Calculating in number of moles of the methane. Okay, the question asks how many grams of each product are formed. So here's where the stoichiometry comes into play. We're going to take our moles of methane and convert that first to moles of carbon dioxide and then to mass of carbon dioxide. And then we'll repeat those steps for the water. So I'm going to take 1.8 moles of CH4 methane. I'm going to convert that to moles of carbon dioxide by multiplying by the mole ratio. And notice for every 1 mole of methane consumed, we're producing 1 mole of carbon dioxide. So the mole ratio is simply 1 over 1. It's a 1-to-1 mole ratio. 1 mole of carbon dioxide produced for every 1 mole of methane consumed. Okay? And then this will get us to moles of carbon dioxide. Finally, to get to a mass of carbon dioxide, we would have to multiply the moles of carbon dioxide by the molar mass. And for carbon dioxide, that molar mass is 44.01 grams per every 1 mole of carbon dioxide. So notice as we multiply across, moles of methane cancels, moles of methane, moles of carbon dioxide cancels, moles of carbon dioxide. And we're left with an answer in just grams of carbon dioxide, which is what we're trying to find, grams of the product. And we get an answer of 79.78, or I should say 79.08, which we're going to round up to 79.1 grams of carbon dioxide. So this would be our answer for carbon dioxide. We're going to repeat the same steps now for the water, the other product. So 1.8 moles of carbon and hydrogen, methane I should say, 1.8 moles of methane. Now the mole ratio is slightly different here. We're producing 2 moles of water for every 1 mole of methane consumed. So the mole ratio is 2 to 1. We have 2 moles of H2O produced for every 1 mole of CH4 consumed. Now we multiply by the molar mass of water, which is 18.02 grams of H2O for every 1 mole of H2O, and we get a mass of water of 64.76 or 78 grams of water, which we're going to round up to 64.8 grams of water. So our two products that we produce are 79.1 grams of carbon dioxide and 64.8 grams of water. Okay, so that's our second problem. Moving on to our third problem. Real quickly here. Okay. Okay, moving on to our next problem. Continuing with the theme of gas stoichiometry. Oops, we can just get the focus. There we go. Okay, number 12. Number 12 says, Fritz Haber, a German chemist, discovered a way to synthesize ammonia gas, NH3, by combining hydrogen and nitrogen gases at extremely high temperatures and pressures. Just to let you know, this is an extremely important in the agricultural industry today. All right, part A says, write a balanced chemical equation for this reaction. Okay, so it says we're combining hydrogen and nitrogen gases. So hydrogen by a gas in the gas state and nitrogen in the gas state are both diatomic. Remember, hydrogen on the periodic table, and then there's that L shape starting at nitrogen going down to iodine, are diatomic gases. So we have hydrogen gas, well, bromine is technically a liquid. Hydrogen gas, nitrogen gas are being combined, and then we are producing ammonia, which is NH3. Now, to balance this, I would first look at my subscripts and notice I have a 2 for hydrogen here, reactant side, and a 3 on the product side. So to balance it, I want to find the least common multiple between these two numbers, which would be 6. In order to get 6 hydrogen on this side, I would put a 3 here. In order to get 6 hydrogen on this side, I would put a 2 here. Now I have 6 hydrogen on both sides and 2 nitrogen on both sides, and now my equation is balanced. So part A, pretty simple. Now part B. If 10 kilograms of nitrogen combines with excess hydrogen at 550 degrees Celsius and 250 atm atmospheres, what volume of ammonia gas is produced? Okay, so first thing I would notice, the temperature and pressure I'm given are for the hydrogen gas. The mass is for the nitrogen. So I'm going to identify what I know. I have a temperature and pressure for hydrogen. So these are both for hydrogen of 550 degrees Celsius, which we add 273. We would get a temperature in Kelvin of 823 Kelvin. Okay? Our pressure for the hydrogen gas is simply 250 atmospheres. Pretty high pressure. What volume of ammonia gas is produced? We're asked for the volume of ammonia gas. Okay. We know our equation, our ideal gas law, is simply PV equals nRT. We know our constant R. That's a given. And we need to find now N, okay, in terms of, we're given mass in terms of nitrogen. We need to find our number of moles for the ammonia. Okay? What volume of ammonia gas is produced? I think I should say these will both be for the ammonia. Okay? The excess hydrogen is part of the reaction, so technically we could say this is for the ammonia, this is for the NH3. Just a little minor detail correction there. Okay, so we're given a mass of nitrogen. We need to find moles of ammonia. So to convert mass of nitrogen to moles of ammonia is where our stoichiometry is going to come into play. Okay, so our 10 kilograms we can convert first to 10,000 grams of nitrogen. Now, to convert the mass of nitrogen to moles of ammonia, we're going to take our 10,000 grams of nitrogen and multiply that by the 1 over the molar mass of nitrogen. I should say, we're going to, a better way to explain that is we're going to divide this now by the molar mass of nitrogen. Notice it's diatomic nitrogen into, so we double the 14.01 to get 28.02 grams of nitrogen as our molar mass. Now we take this value and we multiply it by the mole ratio from the balanced chemical equation, and we can see for every 1 mole of nitrogen consumed, we're producing 2 moles of ammonia. So the mole ratio is going to be 2 moles of ammonia up top produced over every 1 mole of nitrogen consumed. The mole ratio is 2 to 1. So we multiply this all out. This will give us a total of 713.8 moles of NH3 ammonia. So we now have our temperature, pressure, number of moles, and we always have R constant for ammonia. We can simply plug those into our PV equals nRT ideal gas law formula to solve for the volume of ammonia. So when we do that, we have 250 atmospheres for our pressure. We're solving for volume. This is equal to our 713.8 moles of ammonia multiplied by our gas constant R, 0.0821 atmosphere liter per mole Kelvin, and finally multiply by our temperature in Kelvin of 823 Kelvin. Okay. Then we can divide both sides by the pressure of 250 atmospheres on both sides, and this will give us our volume in liters. All right, notice moles per mole cancels, atmospheres over atmospheres cancels, and finally Kelvin per Kelvin cancels to give us our volume in simply liters. All right, when we finish multiplying this all out, we'll get 192.9 liters, which we'll just round up to 193 liters considering some infant figures. Okay, this is our third problem, number 12. So a quick review, we were given the general setup with hydrogen and nitrogen reacting to produce ammonia. We wrote out the balanced chemical equation, noting that hydrogen and nitrogen are both diatomic in the gas phase. We then were given the temperature, pressure of ammonia, where it was reacting, along with the mass of nitrogen. We had to do some stoichiometry to convert the mass of nitrogen in grams to moles of ammonia. Once we have moles of ammonia, we can simply plug our 4 variables into our ideal gas law equation and solve for the fifth, solve for the volume. Okay, atmospheres will cancel, pressure cancel on this side. So we have Our final answer as being the volume of ammonia produced, 193 liters. Okay. And this leads us now to our final problem, number 13. Okay, number 13 says, a 3.25 gram sample of solid calcium carbide, CaC2, reacts with water to produce acetylene gas and aqueous calcium hydroxide. If the acetylene was collected over water at 17 degrees Celsius and 740 millimeters of mercury, how many milliliters of acetylene were produced? Okay, so again, this is one problem where we're going to have to write out the balanced chemical equation first. Then we can identify the variables we know and what we're trying to find. And then finally, we can solve for the volume once we do some stoichiometry. So first step is I would write out the skeleton equation. Calcium carbide, solid calcium carbide, reacts with water, which we know is H2O, to produce acetylene gas, C2H2, and aqueous calcium hydroxide. Now, calcium hydroxide is Ca, hydroxide is a polyatomic OH with a -1 charge. Calcium is a +2 charge, so I'm going to have 2 hydroxide ions bonded to my calcium ion. Okay, now we have our subscripts taken care of. We can balance this. We have 1 calcium reactant and product on both sides. Good. We have 2 carbon on both sides. We now have 2 hydrogen reactants, but notice here 2 and 2 makes 4 hydrogen products. So in order to get 4 hydrogen reactants, I would simply put a 2 here. I now have 2 oxygen reactants and 2 oxygen products, 4 hydrogen products, 4 hydrogen reactants. So now my equation is balanced. Okay, now identify what we know. We know the temperature of the water, which is where the acetylene gas is being collected, so the same temperature is going to be at 17 degrees Celsius, which when we add 273 to that, we get 290 Kelvin. We know the pressure is given in millimeters of mercury, 740 millimeters of mercury. So notice again, we need to multiply by our conversion factor of 1 atmosphere divided by 760 millimeters of mercury to give us a pressure of 0.974 atmospheres. Okay. We're asked for the volume of acetylene, notice, in milliliters. So we're going to have to convert our answer from liters to milliliters for our final step. All right, we know R is always a constant. So the last thing we need for the acetylene would be the number of moles. Now, in order to find number of moles for acetylene, the C2H2, we're going to have to take the mass of calcium carbide given and do some stoichiometry to convert that from grams of calcium carbide to moles of C2H2 or the acetylene. Okay, so I'm going to start off with my 3.25 grams of calcium carbide. I'm going to divide by the molar mass of calcium carbide, which we can find from the periodic table when we add up the calcium, which is 40.08, and the carbon, which is 12.01 approximately. We would get 64.1 grams of calcium carbide. All right. We're next going to multiply by the molar ratio, and I'll just bring this down here, make sure it stays in view of the camera. We're now going to multiply by the mole ratio to get the acetylene gas. We see we have 1 mole of acetylene produced per every 1 mole of calcium carbide consumed. So we're going to multiply by 1 mole of the C2H2 product. We're trying to find and divide by the 1 mole of the calcium carbide consumed. And this will give us 0.0507 moles approximately of the acetylene gas. Okay, so we now have our temperature, pressure, we know R, and we have the number of moles of acetylene gas. So, just a quick note, remember these are all for acetylene. Okay, so to find the volume, we can simply plug into our ideal gas law equation, PV equals nRT. Okay, starting off, our pressure, which we converted from milliliters of mercury to atmospheres, is 0.974 atm. Okay, our volume we're trying to find, that's the unknown, in milliliters, remember. Number of moles is 0.0507 moles. R is our gas constant, we know is 0.0821 atmosphere liter per mole Kelvin. And finally, the temperature, 17 degrees Celsius, is 290 Kelvin. Okay, so we can now divide both sides by our pressure to find volume, 0.974 atmospheres. Divide by that on both sides. Okay. Notice our units. We have to be particular of our units. Atmospheres cancels on the left. Okay. Moles per moles cancels. ATM over atmospheres cancels. Kelvin per Kelvin cancels. We have units of liters. Now this is important. When we multiply and divide, we're going to get a volume of 1.2397 liters. We convert that to milliliters. Remember, for every 1 liter, we have 1,000 milliliters inside. So 1 liter is equivalent to 1,000 milliliters. We multiply and we get a number approximately about 1,240 milliliters of acetylene gas. Alright guys, so this was a quick recap of gas stoichiometry, or quick depending on your point of perspective. So be sure to like, comment, and subscribe. If you have any questions, feel free to leave them in the comments and I'll be sure to try and answer them. Thank you.